This week we have Irene Muzi from Hamburg. We talk about numbers conjecture of directed graphs.
Okay, first of all, thank you for inviting me to give this talk. Right, today I'm going to talk about an elementary bound for Younger's conjecture. But before we start with Younger's conjecture, I should tell you Younger's conjecture is conjecture on directed graphs. I work in directed graphs. But first, before we go to directed graphs, which are a bit complicated, let me give you the undirected equivalent. Now, the undirected equivalent is something that most of us know. It's the Edler-Sposa theorem. Now, the Edler-Sposa theorem says that there exists a function f such that for all k, every graph either contains k disjoint cycles or contains a set S of the vertex set of these graphs, so a subset of the vertex set, such that the size of S is some f of k, and S intersects every cycle. Okay, so either we have k disjoint cycles or a Hittin set of size f of k. Okay, for the Edler-Sposa theorem, the f of k was some O of k log k. So very close between, like a very close dependency between k and f of k. And in a certain sense, this is one of the first results of structural graph theory, because what are we doing? We are excluding some substructure, and we obtain some information on the structure of the graph, right? So you can see it as a structural graph theory result. And now for the directed equivalent, the story is much more complicated. So it was first formulated as a conjecture by Younger. That's why the name. Conjecture. And this was actually proven by Reed. I should say the theorem by Reed, Robertson, Seymour and Thomas. And this is from 1965. 1965 is 1996. It seemed a bit old. So, right. And what's the statement? It's basically the same statement, but for directed graphs. Or I will actually say same, but for directed graphs. So again, we have either k disjoint directed cycles in this case, or a heating set of size f of k. But now f of k in the proof by Reed, Robertson, Seymour and Thomas was a function that is non-elementary. So non-elementary. So first of all, let me explain a little bit what I mean by elementary function. So an elementary function is a function that is either a constant, so this is elementary, and the constant, so the rational powers, exponentiation, and then we have logarithms. We have then, I'm not writing all of these, but trigonometric functions, metric, and then we have inverse trigonometric function, hyperbolic function, inverse hyperbolic. So, and also all the finite combination of this. But f of k here was power tower, 2 to the 2 to the 2 to the 2, blah, 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 blah. A number of times that this is dependent from the input, from k. So some g of k times. Okay? So it's something that, like, before you know k, you don't even know what the height of this tower is going to be. Okay, so not super good, but still a quite impressive proof by Reed, Robertson, Seymour and Thomas.
By the way, what is the growth of GK?
That's just the height of the tower. So basically it's like the so do you understand what I mean by the height?
I understand the tower, so I wonder if
How does G of K grow in their proof?
G of K is like a linear or
I see what you mean, I see what you mean. Well, normally it's like I don't really well, in the case of this theorem, I don't really know what it was. It's usually not so easy to understand because I think in this theorem there is a case in which there is some sort of induction and it's not clear when the induction ends. And so it's not clear how much the tower is long, other than it depends on k. You see what I mean? So it's not always so easy to understand how high the tower is. Yeah.
I think somewhere in the paper they said something like arguments are like Ramsey of Ramsey something, and this is why they didn't want to compute it. So
There's also that, yes.
yes.
There's also the Ramsey of Ramsey of Ramsey of something.
So I
Right.
think G of K grows considerably.
Yes.
Elementary or not?
Unclear.
Unclear, no. But yeah, so we have G of K there. I don't know which one it is. So okay, so finally I can tell you what our theorem says. Oh, there's
Yeah,
3 of them.
right.
Yes.
We can just go all the way to
Nice.
yeah.
Sorry, I had one question. That's when you mentioned finite combinations of these things, you actually meant constant.
I meant constant.
Okay.
Yes. Did I
Because
say
this is a
finite?
finite combination.
I meant constant. Okay. Absolutely.
Yeah.
You will find some definitions online like that say finite. They do not correspond to reality. Okay, so our theorem. So theorem, and this is by so Kreutzer. So simply same statement, but f of k now becomes something of this form, 2 to the 2 to the 2, blah 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 blah, 8 times. Where the last two has also a power that is some polynomial of k. Okay? So considerably.
So double twos is 8? And
Yes. Okay.
No, she just figured it out.
Hmm.
He said it less than 70.
So a little note on how we obtain this. So this result was obtained while we were proving an elementary bound, but for the directed grid theorem. So the directed grid theorem was proven, I will say here, directed grid theorem. I will not bother you with stating it completely and so on. This was proven by Kawarabayashi and Kreutzer. In 2015, if I remember correctly.
Yes.
And this was the directed equivalent of another very important result in structural graph theory, which is the grid theorem by Robertson and Seymour. So the grid theorem basically, this one states that there exists some function f such that every graph of treewidth greater or equal to f of k contains k by k grid. Now, as a minor. So a k by k grid simply is this graph. So this is a 5 by 5 grid. What it means to contain it as a minor, basically, it means that every vertex is mapped into some blob, which is a connected subset of the vertex set. And between blobs that are coming from connected vertices, we have also an edge. Okay, so that's very simply what a minor is. So this f of k was also very big compared to k. So there was a giant effort to actually was that to reduce this f of k wow, come here. Okay. Mostly by basically Shikuri. I'm mispronouncing this for sure, Chuzoi. And I should mention also Tan, who had basically a series of papers that reduced this f of k to some O of k to the 9, and then there was, if I remember correctly, some polylog k. And Well, so how did we start our project to basically reduce the bound of the directed grid theorem, which was also non-elementary, to an elementary bound, was by taking a look at the techniques of Csikszentmihalyi and Tan and trying to adapt them. But we couldn't really do it, right? It required too much symmetricity in the graph, which is something that you really don't have in directed graphs. So we could though adapt one of their objects. So in their papers, they have these paths. Paths of sets, which are very flexible objects, which work a little bit like this. So we have some disjoint subgraphs of G, in which we have two parts, the A and B sides of each of these. This is A2, B2, and then AL, BL. And between them, between B1 and A2, so B, so between, let me put it here, between AI and B I plus 1, now I inverted them, BI and AI plus 1, we have a linkage. So basically, a linkage is a set of disjoint paths. Okay, so between each of them we have these disjoint paths. So they're very well connected, but also A1 and B1, so AI and BI, AI union BI form a Welling set. And what is this set? This Welling set it's a set in which for every two subsets of the set, S1, let's say, and S2, of the same size, we can find a linkage between them. So they're very, very well connected inside here, inside the clusters, and they're also pretty well joined together, the clusters themselves. Yes?
Is this setting in directed graphs?
No, this is in the undirected. Sorry, I should have mentioned, but yes. This is undirected. Okay. So what do we have? Right. We have that in one of these parts
So there's
of...
another question.
Yeah, oh, sorry, please.
I was going to ask, AI and BI are Welling set in the entire graph, or is each blob in its own little subgraph?
They were linked inside the cluster.
In the cluster, I think, right?
So each cluster is its little subgraph, and in there it's a Welling set.
Mhm.
Okay, thank you.
Okay, so what do we have here? Right. We have that these parts of sets, they contain a grid. So I think some part of sets of order something like k squared contains a grid, a k times k grid or something like this. Probably not. Probably square root k times square root k. But anyway, like the bound is very close between these two objects. All right, so as I mentioned, we could do something a little bit similar, right? The object that we find is the following, and now we are in a directed setting, a part of Welling set. So how does it work? We have, again, some clusters. Again, we have some sides. If this is cluster S0, we call this side AS0, and this other side B of S0. This is going to be SL, and then there's going to be A and B side. Okay, so between them, again, we have some linkage that connects them. So it connects B, and this is a directed linkage. So these paths all go in this direction, in the right direction. So we have that BSI is connected through a directed linkage to ASI plus 1. And how are they connected inside? Well, we completely lose part of the connectivity. The only connectivity that we can have is basically connectivity towards the right. So what we say is that basically for all A, B with A contained in ASI and B contained in BSI, so in the same cluster, of the same size, so with A, size of A equals size of B, that is a linkage A to B of size of A. Okay? So we can maintain some of the connectivity, but it's still all left to right. Okay, and what do we obtain? We obtain that a path of Welling sets contains a fence. So it contains a fence. What is a fence? Well, we have horizontal paths, all going in the same direction, so all towards the right. And then we have basically paths going in alternate, vertical paths going in alternating directions. Okay.
Irene?
Yeah.
So this means this path of Welling sets does not witness large directed treewidth on its own, right?
No, I mean, like, yeah.
Okay.
You
But because it does here, then yeah.
Sorry, like
The undirected one does somehow.
Yes, but this is
Just somehow acyclic.
okay. Yes, let me get to the bit where I explain more or less how the proof really goes. So yes, this is obviously the case. So a path of Welling set, we can find it, and also in this case, they, Chikuri, Chozo, and Tan, found it in the case of large treewidth, right? So again, for us, we are talking about Erdős-Pósa. We have two cases, one in which we contain a fence, and in fact, we also contain a fence with the last bit, like the ends of these paths, connected through a linkage to the, it could intersect, of course, I should have used another color, to the starts of the linkage. Okay, so that's the fence that we have. And we have a lemma from the work, from the previous work, right, of with Robertson, Seymour, and Thomas. Lemma. That says that okay, that if we have a sufficiently large fence, if we have a sufficiently large fence with let me call it somehow. So the fence is defined, is called like QP, where for, let's say, Q is going to be the horizontal linkage and P is going to be the vertical one. We have what? We have, so if we have a sufficiently large fence QP with the end of, let's say, Q connected through a linkage to the start of Q, then it contains k disjoint cycles. Right? Okay. So in this case we're done. Right? If we have this case, we're good. So what happens in the case of low treewidth, right? Because that's what's missing here. In the low treewidth case, we have another lemma. This is by a work of, so let me write, lemma. This is a work by Amiri, Kawarabayashi, Kreutzer, and Wallen from 2016.
Oh, I have a question.
Yes?
So this is low tree case, that means if the graph is large trees, then it contains a large fence.
Yes, it will contain a large fence in there.
Here, when you have a linkage from the end to the start, do you follow the ordering, or ordering doesn't matter?
No,
first
he
pass-
did, as far as I remember, the ordering doesn't matter, no.
So the first can go to third. and
Yeah.
to, I see.
So, okay. Also, they can like very much intersect the whole fence. So,
If the ordering doesn't matter, can't I do like an Escher fence?
what do you mean?
Then you will only get a single cycle, right? If I twist the linkage completely, make it disjoint from the fence.
Wait a sec.
Uh,
So you make it disjoint from the fence and then you twist it around. I suppose it's possible. Let me see. Maybe the ordering does matter.
And it should be fine if you go through the cross step twice, you can unwind and find a large pattern again. So
Oh, you're right.
it can happen, but it
You
doesn't
just
matter.
always means
Sorry.
one inwards.
Sorry.
Okay. So that's fixed. Thanks. Okay, so fine. This lemma, the low treewidth case. So they were doing something a bit more general. They were looking at the Erdős-Bosa property for graphs, or well, in particular for topological minors, of strongly connected graphs. So strongly connected digraphs. So I will have to explain something about this. So that the be a digraph with the directed tree width of D being less or equal to W, then for each strongly connected, can I write it like this? Strongly connected digraph H, the digraph D has either K disjoint copies of H or again a hitting set or a hitting set of size at most K times W plus 1. Yep. So by a hitting set, of course, I mean a set intersecting all these topological minors. This is as a topological minor. Let me not explain you what a topological minor is. What I can tell you though is that this graph C2 is a topological minor of Ci for all I.
The cycle length I, right?
Huh?
Ci is cycle.
Ci is a cycle. Yeah. Sorry. So, since this is a topological minor of any Ci, when we take H to be C2, we get that we either find K disjoint copies of, well, K disjoint cycles, or a set hitting all of them, right? So, I finished the words. Okay. So that handles the low tree-width case. So let me explain a little bit what we did for the large tree-width case, right? So more or less as in any of these cases, we get that we start with a Welling set. So what is a Welling set in a directed setting? So we start with well linked set. So a Welling set is a set in S such that for all A, B contained in S, a set S contained in the vertex set of the graph, of course. For A, B contained in S, with again the usual condition that they have to have the same size. We get a linkage from A to B and a linkage from, let's do it in the other direction, B to A. Okay? These two can intersect each other. The parts in one of them, so two parts in one of them cannot, right? So this distinction should be made. And of course we can find the Welling set in a high treewidth graph. So if we have high treewidth, then we can find the Welling set. Okay. So now, from the Welling set, what both the in the paper of Reed, Robertson, Seymour and Thomas, and also in the paper by Karabayashi and Kreutzer, the directed grid theorem paper, we have that they start from a web. They both obtain a web. Now, in the case of Karabayashi and Kreutzer, it's a bit more unclear because we think we have found a problem with the proof of their obtaining the web. Yeah. So, I mean, it's unclear, but we have another beautiful and shiny proof of that, which I'm not presenting today, but is present on arXiv and we published already in Fox. And basically, what is a web? So for us, the definitions sort of change a little bit from paper to paper, but for us it's going to be just the following. Maybe I can write it here actually. So we take a digraph, and then two linkages. L and H. Oh, actually, let me call them H and V. So, as the name suggests, one is horizontal, the other is vertical, or considered so. It's really like the web is a bit messy. I'll show you in a second. So these are size of H, size of V web. If which we call HV, if every part of H intersects every part of V. Okay? So this is a very messy object in a sense, that sure, this you can write the first part horizontal, and you can think as V as vertical, but the reality is that we can do the weirdest thing in there, right? As long as they intersect all the parts.
Oh, I have a question.
Yeah.
Does intersecting at the endpoint also count?
Yes. So
Okay.
wait a second. What do you mean intersecting at the endpoint?
So they just share an endpoint, and you
Yes.
consider them as web?
Yeah,
Oh.
absolutely. Okay, so, all right, but we are actually able to order them a little bit. So in our proof for the web, we actually obtain something called an ordered web. I think I need to delete this one. So an ordered web, well, definition by picturing in a sense. It's going to be some web in which we split the, oh, come on. Let me try this. The horizontal parts we split them in sections, and then for each of these sections, like if this is section 1, V1 is only allowed to intersect into this bit. V2 only in the second part, V3 only in the third, and so on. Okay? So, where do we get this web from? We get them, we said, from the welding set, right? And in fact, because we take them from the welding set, we can make sure that the last vertices and the start vertices are taken from a welding set. So they will also have a back linkage. Okay, so a linkage that goes from the ends here to the starts somehow. And of course, it can intersect the web however it wants, even if I'm drawing it disjoint. Okay, so because of this sort of ordering, this is starting to look a little bit like another object. And this was a little striking to us. So remember that we want to obtain in the end these pulse, this path of length of welding sets. And what we wanted to get is some sort of connectivity from, let's say, from the left to the right, right? So we need to sort of figure out how to make it happen inside this web, how to obtain a pulse from a web. And the way we did it is by using this concept of temporal graphs. Okay, so what are temporal? Well, I'll say digraphs because that's what we use. But the concept is defined for the graphs as well. Well, temporal digraphs are a pair. V curly E, or where V is a vertex set, and E instead is a sequence of edge sets. I don't know, L? Let's say L. Okay, and it's such that one of the layers is a digraph. For each layer, you have this pair is a digraph. So V, E, T. Okay. So what are we saying by this? We have these layers, and what does it mean that it's a temporal digraph? We have that, basically we have our vertices, but the edge connectivity, like the edges in these digraphs, they change through time. So we consider each of these a time step and the edges are going to change a little bit. Let me try to give an example. Something they could change like this, right? Sometimes they're not even connected. Okay, let's say that. So imagine that I want to find some path that goes from A to B. And I want the temporal path. What am I allowed to do? I'm not allowed to take two edges in the same layer, because what we're assuming is that once I make a step, I'm also going forward through time. So basically, I'm allowed to take this edge here, and now I'm here. And I'm not allowed to take this edge down anymore, because it's not existing anymore. So I need to go right. In here, I can go down. It's not important that I'm not connected to B, because in the last one, I am. So this is what a temporal graph is. Of course, this in the temporal digraphs are all directed.
And would you be allowed to be lazy and sit on a vertex for a couple of steps and then take the next one?
Let me think for a second. I think we allow this. Yes, we do allow this. I mean, but I think you can, take the definition that you like. But in our case, we do. Okay. So how do we go from webs to temporal digraphs? Well, we have these paths, and in a sense they provide a timeline for our temporal digraph, in which each of the layers is going to be a different path of the vertical linkage. Or so, at least at the start. We also use them later for other stuff, but this is what happens initially. So here, for instance, if I call these guys like H1, H2, and so on, here I have H1, H2, let's say H3, H4. And what did I draw? There? I drew something like from H1 I can go to H2. From H2 I can go to H3. Then I can also go back to H2 from H3. And from H3 I can go to H4. Right? So this would be my first layer. And what we are able to do is we're able to identify an object. So we identify an object called an H routing. H is not the same H as here, just telling you. An H routing. H is going to be a digraph, which encodes connectivity in a temporal digraph. what is an H routing? Let me give you a definition and then I'll explain a little bit. It's not a super easy concept initially. So definition of H routing. So we take H, a digraph, and D, the container, let's say. It's either a digraph or a temporal digraph. And S, some subset inside of field. So an H routing over S is a bijection phi from the vertices of H into S, such that for all UV path P in H, we can find phi U phi V path in D, which is also disjoint, and this is important for later argument. It's going to be disjoint from S minus phi of V. So you're only going to use the vertices of the path. Okay, let me explain a little bit about these objects. I think this would be a good board. So first of all, notice that I said for all UV path, we can find the phi U, phi V path in D. The reason why we're taking paths is that connectivity is not transitive in temporal graphs. So for instance, if you have two layers like this, so where this is A, B, C, A, B, C. Well, we have that B and C are connected. We have that A and B are connected. A is not connected to C though, because this guy is at a different step, right? So really for each path we need to get this other path in there. Okay, so let's see. Right. So in our case, we wanted to find connectivity in a cluster from the left side to the right side, right? For each, so this is a cluster. For each of these subsets of same size, right? And what we found basically is that if we get CK or bidirected PK routing. We have this connectivity. We have that we can find these welding sets basically. I'll write it very abstractly, but I don't want to get into the weeds of that proof. Yes. Okay, this is like the part where we get the Paul is actually, going through many different objects, and it's probably the most complicated part. What I'm going to tell you now is how to get to the fence. But first, before we do that, I need to give you a lemma, and then I'll give you a recap of what the proof actually looks like. Okay, so we need a lemma to prove the next bit. And I'll call this lemma 1. So let n of kp be equal to 2k squared p cubed. Every strongly connected digraph D with the size of the vertex set at least n of at kp contains either PP subgraph or a K bidirected click on K vertices routing. Okay? I should say over some S in VOD. Okay. So we have this lemma. Let me recap a second what the proof looked like so that we know where we're going. Didn't want to do that. Maybe I'll destroy another one. Yeah, you're not gonna see that anyway. So, the recap is as follows. So, remember that we started with high directed treewidth. From this we obtained a Welling set. From the Welling set we can obtain this ordered web. And remember that there's going to be some back linkage. And from the web we said we can get this path of Welling sets. And this is through the use of our temporal digraphs. Temporal digraphs techniques. And what we still need, is what? From these part of Welling sets, we're going to obtain a fence. And from the fence, because of the lemma, but read Robertson, Seymour and Thomas, we obtain the decay disjoint cycles. So let me talk a little bit about this part. Let's see. Yeah. Just there. So what we're going to prove is the theorem that goes as follows. Every part of Welling sets S, these are the clusters of the Welling set, and this is the linkage between the clusters of greater than some function, which I can give you if you want, WPQ, and length, I cannot write today, length L, now greater than some other function that I can also give, PQ, contains a PQ fence PQ, and moreover we can find the start of Q contained in A of S0 and the end of Q contained in B L, well, B of S L. Okay, why these two? This is going to be the reason that we highlighted before. We have found this part of Welling sets in a web, right? We have found it in a web, and what we want, what we can find is that this part of Welling set starts and ends in the start and end of the web, and since the web was connected with a back linkage, or well, actually since the web, this ends and starts come from a Welling set, these are coming from a Welling set, we have that the start and end of this part of Welling set is also connected with a back linkage. Okay? So the back linkage can intersect this object, but it's there, and that's all we need. Okay. So define linkage. Right. So that's what we want to prove. Okay, so the first thing that we want to do, and I hope that you find that this is reasonable, inside the path of Welling sets, we're going to find a linkage that goes through all the Welling set, the path of Welling sets, until the end, the last B set. So we find this linkage L of order, let's say K. Okay, is this reasonable enough? I mean, the clusters themselves are very well connected, and we have linkage between them. So I hope it's clear enough that we can do this. Now we're going to take these as the layers of our temporal graph, and we're going to use these kind of techniques again. So these layers, as we were saying from the lemma that I just removed, is it here? Yes. Let's do it like this so that you can see the lemma. So we need that these layers are strongly connected. So for each one of these paths in the linkage, we want that they are connected between each other. But this is fairly easy because if you have two paths, they're going to hit the B side, the A side and the B side of each of the clusters. And now, if I want to connect this first one to the second one, I have a connection given by the definition of the path of Welling sets, and second one to first one as well. So remember that for each subset that I have in A, I can find a linkage to a subset of the same size in B. Okay, so every layer is strongly connected. And then I can use the lemma 1, right? Now lemma 1 says that I can find a PP subgraph or a KK routing. But that means, really, what we really need in this case, we need a PK prime, say, routing. Now, why do we need a PK routing? And let me first convince you that that's what we get here, because a PK routing will be included in a KK routing, and also any PP subgraph is also a PK routing, a PP routing. So what do we have? So at this point, what we want to really do our technique is that we take these layers and in each of them we find some path, some temporal path, right? And we want to concatenate these. Let me remove this last bit. We want to concatenate this to obtain an acyclic grid. The important part is that we found a KK routing. Let's see if I still have the definition somewhere. No. But the important part was that, as I was saying, we're only allowed to use vertices of the routing itself. So we are not allowed to use these other paths. So if the path intersected anything here, that would be a problem, right? But because we found the PK routing, we're not allowed to do it by definition, and so we can actually sort of make this into an acyclic grid. To tell you exactly what an acyclic grid is, it is this object in which we have two linkages intersecting exactly like this, and one always going from left to right, the other from top to bottom, right? So there are no cycles in here. And now what we want, the last bit of our theorem.
I hope it's really last because it's now overtime.
Oh, it's overtime. Okay, sorry. I thought I had more time. Okay, so the last bit is that we really need these temporal paths to be the same in each of these. So this path here in red, it needs to be the same. Use the same parts of the linkage, right? So what we're going to do is take the linkage gigantic, and then take the linkage gigantic and then use the pigeonhole principle to find some M that match. Okay, so that was really the last bit, other than, well, from here you can find, in here you can find the fence. And here you'll have to believe me because I'm over time.
Okay.
Oh yes, I'm definitely over time, sorry.
Maybe
Sorry.
one quick question. Yeah, Max.
Are there any reasonable lower bounds either for the directed grid theorem or for Younger's conjecture?
So for Younger's conjecture, I actually don't. No, I don't know any of those. Right. For the grid theorem, I thought about it a little bit. Someone drew a picture about this, but I think they're not reasonable. Like they are k cube or something like this. They're very low and.
We know K cube.
So.
We know K
We
cube.
conjecture K cube.
Yeah.
There's a picture.
There is a picture with k cube which has not been checked yet. We can probably do k square. Like I mean, if you take a
K square should work. Yes.
like yeah.
Just from the undirected stuff, right?
Yeah, basically same as the undirected stuff. Yes, they're super unreasonable. Like they're super low. Consider that for the directed grid we get a tower of height 22, I think, and we have a lower bound that is like a cube, but most. Like, so. Yeah.
All right, let's thank the speaker.